1.4 is on rational functions. Now remember that there's lots of different kinds of functions. There are linear functions, there are quadratic functions, there are exponential functions. These are different function families. And the idea is that when we're all mathematicians going through life and trying to better understand what is happening around us, and it's helpful if we can, when we're looking at something, it's helpful for us to be able to identify it as a specific function family. Now, this is one of the activities that we have in secondary math 3. This is a calculus class, but I'm going to pull out this activity anyway. So let's say that there's a gift and the gift costs $360. Now, $360, I want to buy this gift for say somebody's quinceañera, but that seems a little steep for me. So this is the cost, and this is over here. Well, for our X value, I'll write number of people. And if it's just me paying for it, it's going to cost me $360. And as I said, that's way too expensive. So I ask Bryn, I say, Bryn, Kitty, can you go halvesies on this gift with me? Nice. And Bryn says yes. And so if Bryn and I both pay for this gift together, then we're both paying how much each?
180.
180. Yep, we're paying 180. Do you remember this activity from last time, Bryn? I don't know if you do. It was a while ago. That's fine.
I don't think it was this exact number, so I think this might be the same scenario that you used
Okay.
on the quiz last year.
What if I get another person? How about Bentley? Bentley decides to go in on us. He's like, oh yeah, I wanted to buy a gift anyway for this individual. And so, yeah, I'll go in and split the cost with you. How much does each person have to pay now?
120.
120. What if 4 people? What if we can get another person? How much? I couldn't hear you.
90.
Oh, it's 90. Yeah, I agree with you. It's 90. So each person spends 90. What if we can double that? What if we could get another 4 individuals to join us?
45.
Yeah, it's going to be 45. So the relationship, as one value over here goes up, the other value over here does what? It goes down. So we have this inverse relationship. Can you think of an equation that would represent what's happening here?
Divided by X.
Yeah, so we have y equals 360 divided by x. If I plug in 1, then I get this 360. If I plug in 2 here, I get the 180. Do we agree that this is our equation?
Yes.
Okay, now what you should notice is what we have a fraction. In fact, more specifically, we have a polynomial over a polynomial. We have a polynomial over a polynomial. In fact, that's the definition of a rational function. When you have a polynomial divided by a polynomial, it falls into the function the function family is rational functions. Now there's a whole, in fact, what we could do is describe all right, so I don't know if I'll talk about that right this minute, but I guess maybe I will. So this is sort of how we would define so a rational function. Gosh. Well, now it's not letting me write it at all. Something just happened, not responding. Just great. There we go. Okay. A rational function all right, so this is 360 times x to the power of what? 0. That's why 360 is a polynomial. What's a polynomial? The way I tried to describe it, the way I tried to define it was multiple terms, right? Right? Now, this is not multiple terms. How many terms is this?
1.
It's 1. So I suppose you would still classify it as a polynomial because we could have all these other terms back here, like, I don't know, how about plus 0x to the power of 2 plus 0x to the power of 3, something like that. So we'd still call it, sure, it's a monomial, but we can still categorize it in the group of polynomials. Right, so rational functions are defined as a function where we have a polynomial divided by another polynomial. And here's sort of an idea of so if I have, y equals a, which is some coefficient, some number in front of our variable, and then we have x to the power of n. And the way we write a polynomial is in descending order of exponents. So the next one would be, I don't know, how about b times x to the power of what, if we have descending orders of exponents? This would be n minus 1, yeah. And then plus, I don't know, c times x to the power of n minus 2, yeah, plus dot, 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 over some other polynomial. We'll say the leading coefficient is L times x to the power of m, plus, how about m times x to the power of what? Yeah, m minus 1, we have descending order of exponents, plus n times x to the power of? Yeah, descending order of exponents. That's really the definition of, I'm sorry, what?
Do you mean to have what was the next one?
Oh, I see the confusing part. Yeah, what if we change that then? Yeah, so what Brendan's saying is that it might be confusing because we're using, are these numbers related? And I didn't really mean them to be related. I suppose they could be, but I want to make this more generic. So yeah, I agree. I might just saying for sure these, or I want to say that they don't have to be the same. I think that's more of an important thing to say. So instead of n, how about p and q? Is that better, Bryn?
Yeah.
Yeah, I like it better as well, because there's no confusing about those variables. All right, so let's go ahead and do some, I want to talk about like simplifying. In fact, it seems suspicious, like these rational functions. Seems like fraction functions. Doesn't it feel like a fraction function? They're very closely related. In fact, everything that we do with rational functions, we could do with fractions and vice versa. So let's look at, like, if I simplify 15 over 20. Now, the way I know you have a different way of simplifying. You probably look at both of these and you say, well, they're both divisible by 5. And so I'm going to just simplify it that way. How many 5s go into 15 and how many 5s go into 20? But I want to encourage you to think of it this way about factoring. Let's factor the numerator and factor the denominator. If we factor the numerator, what do we get?
3 and 5.
right? We get 3 and 5 and 5. If we factor the denominator, we get 2, 2, and 5, or just 4 and 5. 2, 2, and 5 is 5, but I sort of like the 4 and 5 because the next step should make it, as far as simplifying it, the connection between fractions and rational functions will be easier to make. So any guesses what we'd do at this point to simplify? Yeah, what is 1 divided by, what is 5 divided by 5?
1.
It's just 1. So, and what is 1 times 3/4? Yeah, just 3/4. So we can eliminate these, and then our answer then is 3/4. So I want you to think of when you get a problem, a rational function that, or maybe a rational expression that you need to simplify. I want you to think of factoring first before you simplify. So let's do an example of a rational expression. Here's our example. I have 9x to the power of 3, or cubed if you'd prefer, over 27x squared. How would we simplify this?
This first one, split it up like we did it.
Yeah, I really think it's easier for understanding when we do that. When we have the 9, for example, can be broken into 3 times 3, and the x cubed, if you want to, can be written as x times x times x over what? If we break that up,
3, 3, 3, x.
3, 3, 3, x. What can I eliminate? Yeah, x divided by x is
1.
and x divided by x is
1.
and 3 divided by 3 is
1.
and 3 divided by 3 is
Pretty sure that's 1.
okay, which gives me what?
X over 3.
X over 3. Yep, x over 3. Now I also want you to consider one of the laws of exponents. Now remember, the definition of an exponent is just what we do when we're multiplying the same number. If I have something like 3 plus 3 plus 3 plus 3, well, that's the definition of multiplication, 3 groups of, right? Or groups of. So this would give me 3 groups of 4 in this case. That's really what the definition of multiplication is. But what if I'm multiplying? What if I have 3 times 3 times 3 times 3? Then the definition of an exponent is what? How can I rewrite this to simplify it?
3 to the power of 4.
3 to the power of 4. Yep, 3 to the power of 4. Now, based upon this simple concept, mathematicians have seen patterns. And based upon those patterns, they've come up with laws. What is the law for this one here? If I have the same base, and what do I do? I have the same base and I'm dividing. What do I do to the exponents?
Subtract.
We subtract. Yep. So in this case, our law is a to the power of b over a to the power of c is a to the power of b minus c. So we could do that. We could just take care of that to give x to the power of 3 minus 2 would give us x to the power of 1. And that's what we have here is x to the power of 1. All right, let's do another example. I have x squared minus 9 over x squared minus 6x plus 9. This is, I'm going to warn, actually, I'll give you some think time. I'll give you a little bit of think time. This is what students want to do all the time. This is the temptation for all students to do this. Is that okay?
No.
No. We're not multiplying. That would be equivalent if I had 15 divided by 5. I rewrite this as 10 plus 5 over 5. I cross these out and I get 10. Does that look right?
No.
So what was the problem? You can't eliminate.
When things are being added.
Yeah. Yeah, we eliminate factors. We don't eliminate sums. You cannot eliminate sums. We eliminate factors. So if you're tempted to do this, get that out of your head. That is not allowed. Bentley, what do you do instead?
Could probably watch videos last time.
I tell you what, I heard you say I should watch the videos less.
Last night.
Oh.
I'm guessing factoring so that we can.
You do factor. You do factor. How do I factor this? Yeah, this is a special factor. What's the name of the special factor?
Difference of squares.
A difference of squares. That's not a square. Yeah, it's 3 squared. So I have a difference of squares. A difference of squares can be written. So if I have a difference of squares, the difference of squares can be written how? Or is it more helpful if I write it? Yeah, x minus 3 and x plus 3. Yep. Over what? X minus 3 and x minus 3, right? So what do I do at this point?
Take out and two the x minus 3 on top of the x and 1x minus 3 on the bottom.
So we get x plus 3 over x minus 3. Would you agree? Is that good? Now, because I'm eliminating the same thing, normally I would have to capture that loss there and say x can't be 3. But excuse me, but I don't have to do that because it's already implied here. It's already implied that x can't be 3. Why can't x be 3?
Because then the bottom equals 0.
Then the bottom would equal 0. So I don't, do you see how I don't have to have this? Even though this has been eliminated, I don't have to have this because it's already implied in my answer. So I'm going to take that away for, I'm going to take it away. I think the next problem we will have to do something. Well, here's my example. So what was that? Was simplifying, right? Simplifying. Next one is multiplying. Let's go back to 4th grade. 4/3 times 3/5. What's the rule when we multiply fractions? Or how do we do this? I can think of 2 different ways. That's why I'm going to leave it up to you. How do I do this?
Cancel the 3's.
Okay, we can cancel out the 3's. What is this called? It's not cross multiply. Cross multiplying is this: 4/5 equals x over 8, and we cross multiply here, and we cross multiply here. It's actually cross simplification. It's called cross. This is cross multiply. Cross multiply. And we only cross multiply. The only time you'll ever cross multiply is when you have a fraction equals a fraction. If you don't have a fraction equals a fraction, you will not cross multiply. So this is called cross simplification. We are simplifying crossly or diagonally. So what's my answer?
4/5.
Yeah, 4/5. Let's do an example. What if I have, here's my example. 3x minus 12 over x plus 5 times x plus 6 over 2x minus 8. What are the directions? Multiply. Directions are to multiply. Where's Eileen? Did Eileen ever come? No. Where's Damien? Eileen's here? Oh, question? Do you have a question? Okay. Damien, where's Damien? Damien, nice. Where's Natalie? Natalie? Where's Ethan? Where's Christian? Where's Kyler? Where's Julian? No, Julian. Where is Anna? Gabby. Do we have the answer to this? What did we do first? Gabby, what did we do? All right, so what can I factor? Can I factor this first piece here at all? Excuse me. Not at all? It looks like I could factor something out of both terms. All right, so I'd have 3 times what? Okay, over x plus 5, right? Out of this? Out of this too? I cannot take out an x because there's not an x here, right? Okay, so I'm going to take out a 2. What's left over? Okay, what can I do now to what can I do now? What did we do up here? Yeah, we cross simplified, so I can eliminate this piece here. Can I do anything? What about this? Can I do that? Can I eliminate those? Why not? Because it's addition. Good. So we can't really do anything else, right? So that gives me what? 3 times x plus 6 over x plus 5. What happened to the 2? Does that look right to you?
Yeah.
Okay. Now there's one problem that I have here. There's something that I'm missing here, comma, x cannot be what?
4.
It cannot be 4. I really need this extra piece here. Otherwise, they are not equivalent. Because if I plug in 4 here, what do I get? Don't I get a 0 in the denominator? Can I have a 0 in the denominator? No. In fact, why don't I graph both of these? I'm going to go to Desmos and graph both of these and see if they are indeed the same. So I'm going to treat them, right now they are an expression. Why are these, why is this an expression? That's not equal to anything. Now, just for graphing purposes, I'm going to make it equal y. Okay, just to have a graph. So just for graphing purposes, I'm going to add that extra piece to both. So I'm going to go to Desmos. Okay, I'm going to type both of these in. This is my original. So I have y equals, these are just placeholders for now. I have 3x minus 12 over x plus 5 and times x plus 6 over 2x minus 8. So we have this graph here. And then, so this is our graph right here. And now I'm going to type in my next one of this one here. Y equals, and again, placeholders. And then I have this 3 and then parentheses x plus 6 in parentheses over 2 times x plus 5. Did Mr. Hall lie to us? They are the same. What? Well, why even have that extra piece in there that says x can't be 4? Should we get rid of that?
Yeah.
No. We're not going to get rid of that. And why is because which graph do I have to add x can't be 4? The blue one. Let's look at the red one. I'm going to take away the blue one. We're going to look at the red one. I want to look at what happens when x is 4. So I'm going to here. How many solutions are there here on this graph? Infinite, because it's solid. It's solid, and that tells me that there's infinite. I'm going to go over here and see what happens when x is 4. What happens when x is 4?
Undefined.
Says it's undefined. Why is it undefined?
Because 0 is in the denominator.
Yeah, because it'll give me 0. If x is 4, it'll give me 0 in the denominator, which is not allowed. Does that hole at 4 exist for the blue graph?
No.
Let's look at the blue graph. I'm going to go over to 4. X is 4. Does the hole exist for the blue graph?
No.
So to say that both of these, let's see, let me go back. To say that both of these expressions are equivalent, do you see I have to have this? Why was there not a hole? When I graphed this, why was there not a hole for x is equal to 4? Because what did I do?
You took away the thing that made it so that.
Yeah, I eliminated that. Yeah, I eliminated that. So to be completely honest with our math, we have to say x cannot be 4. Okay, moving on. Unless you have a question. Does this remind you of secondary math 3? Some of the stuff we're doing? What's the rule when I divide? Yeah. So we keep the same function. Keep the same fraction, 3/4. We change the division to multiplication. And we flip 4 over 1. That equals, well, at this point, we could multiply 12 over 4, or we can do what? Or
Cross simplification.
cross simplification. Cross this out, we're left with 3. The answer is 3. I'm a little bit, what I would like to do is spend a little bit of time in class showing the video. In fact, I just wonder whether if yeah, maybe I'll show it. Actually, I'm going to upload this to YouTube. So I think that if I showed this, then YouTube is going to end up banning the video. But there's a video called keep, change, change, flip. And it's posted on for my videos, keep, change, flip. Bentley, did you see it when you watched the videos?
No.
Oh, you didn't see it. Okay. So anyway, I don't want to show it right now because it's going to, I think YouTube will block my video if I do that. So anyway, whenever we divide by fractions, here's a tip. Keep, change, flip. When we divide by fractions, here's a tip. Keep, change, flip. Again, everybody, when we divide by fractions, here's a tip.
Keep, change, flip.
Nice, cool. All right, so what if we have something like this then? I have x squared plus x minus 6 over x squared plus x, and I'm going to divide by x plus 3 over x. What do I do? You want some think time? Think time?
Yeah.
Cool. Right now is a great time to get some repetition, some challenging. Well, this is how you develop your math. Otherwise, if you're just watching Mr. Hall do the math, it would be equivalent to sitting on the slopes, watching other people snowboard, and then think you know how to snowboard. Where's Carter? Where's Ian? Where's Lachlan? Where's Gaia? Where's Evan? More think time? Raise your hand if you want more think time. Okay. Natalie, where do I start?
Once you simplify, well, you flip and change the symbol.
Okay, so which one, the first fraction or the second fraction, or does it matter?
You flip the second one.
Good, it has to be the second, good. So I have x squared plus x minus 6 over x squared plus x times x over x plus 3. Nice. Nate, what do I do next? Okay, so factor this to get what? Nice. Where's Jack? No Jack. Okay. Damien, now what?
Now we would.
Is there something I can do with this, Damien? Factor what? What can I factor out of both of these terms? Yeah, I can factor out an x. What's left over, Damien, when I factor out an x? Do you agree, Damien, that this is x times x plus x, right? If I factor out one of these x's from both of those terms, what's left over? Okay, I have x and 1. Would it help if I wrote this? I don't know if that helps. Isn't that 1x? Does that help, Damien? All right, so this is plus 1. How can we check to make sure we did it right? Yeah, let's distribute back. Let's distribute back and see if we get the same thing. Damien, do we get the same thing when we distribute back? Yeah. Cool. So we know we did it right. On, did you say, does it matter which order? Wait, did I hear the?
I'm just wondering, like, could you actually show the steps?
Yeah. Huh? Okay. So you want to know how I got this? All right, so what I did, remember that our formula for this is, so this goes with, this is a quadratic that's fairly easy because my leading term is 1. When my leading term is 1, it's fairly easy to factor. When it's not 1, it becomes more difficult. In fact, I'd almost be tempted to use the quadratic formula for that, just to figure out what the zeros are, and then you could make those into factors by, reversing your variable, your operation. So what I'm going to do is, so this is a 1 right here, right? And it agreed. Do you agree that that's a 1? Okay. Now I'm trying to think of two numbers. So if I have, let me use a different color. If I have x squared plus bx plus c, and I'm trying to factor this, I'm trying to think of an n times an m that gives me what? Yeah, to get me my c value, in this case, my -6. And I'm trying to think, and those numbers, when I add them, have to be what? They have to be b value. In this case, it has to be 1. Does that make sense that those n and m values are 3 and -2? Because 3 and -2, when I multiply them, I get -6, but when I add them, I get 1. So there you go. Okay. So on the other side, I still have this. Was that good? Are you all right?
Yeah, I didn't realize that we were still factoring, and I thought this one was wrong.
Oh, I see. And so on the other side, I have this x over x plus 3. Where do we go from here? Yes, Natalie. Get rid of the x, okay, because x divided by x is what? It's just 1. And then x plus 3 divided by x plus 3 is? Leaving me with what? What's my answer?
X minus 2 over x plus 1.
Okay. Is this equivalent to this?
Yes.
There's something that this has that this doesn't have.
X cannot be equal to -3.
Good. There's actually two things it can't be. It is true that x can't be -3, and
It can't be -1.
well, that's already implied, right? It's already implied here that it can't be -1. It can't be 0. It cannot be 0. So 0 is also something we say that it cannot be. Because what happens if this is 0? That would be 0 times something, and whatever this is, and 0 times anything is 0. So it can't be 0. So that's my answer. That is my answer. Are we good? Questions? Yes, sir. It can't be -3 because if this x right here is -3, then I have -3 plus 3, which is 0. And why can't you have 0 in the denominator? It's undefined. Yeah, it's undefined. What happens if you ask Siri if you divide by 0? Cookie Monster has no cookies and you have no friends.
Yeah. Don't.
Just don't ask her. Don't ask her. Yeah. All right, so let's move on. Let's do adding and subtracting. This is the most difficult part. Let me use black. Adding, subtracting. I have 1/2 plus 1/4. So remember, everything that you learned back in, well, some people said 7th grade and 4th grade. And Brandon, when did you learn fractions? Just curious.
I don't know. I think like I know I was working with them in 5th grade, but I don't remember they were introduced in 5th grade.
Okay, so at least 5th grade, right? At least 5th grade. So we have this 1/2. And I'm going to add it to a 4th. And we can almost visualize that we take this 1/2 and then we take this 4th and move it over here. And then that gives us how much? 3/4. How do we do it algebraically? We have to have, when we add or subtract fractions, we have to have a common denominator. So I'm going to multiply by what? We're going to multiply by 2. Doesn't that give us 1 plus 1/4?
2/2.
Yeah, we're going to multiply by 1 because whenever we multiply by 1, the cool thing about multiplying by 1 is nothing changes, right? That's the cool thing about multiplying by 1. So I'm going to multiply by 1 in the form of 2/2. So that's going to give me what? What does that become?
2/4.
Okay, it gives me 2/4. Now we have a common denominator. When we add the common denominator, do we get this? Do we get the same answer? Yep. So we get this 3/4. We get the same answer. All right, same rule when it comes to rational functions. In this case, we're not doing functions. We are doing expressions. So let's do an expression. What if I have 2/2x plus 3/2x squared?
By x/x.
All right, so we're going to multiply it by 1 in the form of x/x. So I have x/x, okay? Now what? Now if I multiply that, gives me 2x/2x squared plus 3/2x squared, okay? Now what?
That's the common denominator.
And what?
You add
Oh.
the common denominator. We add the stuff that have common denominator.
Yep. So that gives me 2x plus 3/2x squared. This isn't, those are not like terms, right? So we can't really combine those. And there you go. Okay, we're good. Why can't I just eliminate these two? Because of adding. I know that's so tempting for students, but because of this adding, we cannot eliminate. We no longer 2 is not a fact, it's not a factor, right? It's a factor of this expression, but it's not a factor of the whole numerator. Do I need to eliminate anything? Do I need to say x can't be something?
You don't need to say it.
Yeah.
Implies it too.
All right, I didn't eliminate anything, right? So we don't have to write anything there. Agreed. Anytime you eliminate something, see how up here, I eliminated these x's. So that means that my next expression doesn't tell me that x can't be 0. So I have to add it. Do you see how I'm eliminating this x plus 3 and x plus 3? So now there's nothing in this expression that tells me that x can't be negative 3. Does that make sense? Or is it confusing? Makes sense. Okay, cool. Let's go down here. Let's try another one. Here's our next example. I have x minus 2 over x squared plus x minus 12 minus 1 x over x minus 3. Winnie, where do I start? Yeah, we need to factor this. You are correct. And so what do I factor it to become? Okay. Anna, now what? What's the rule when we add and subtract fractions? We have to have a common denominator. How would we get a common denominator?
Multiply by 1.
Yeah, we need to multiply by 1 in the form of what?
X plus 4 over x plus 4.
Yeah, if I multiply over here by 1 in the form of x plus 4 over x plus 4, do you see, Anna, that we have a common denominator now? Once we get a common denominator, what do we get to do? Yeah, we just subtract the numerators. So that gives us x minus 2, the quantity of x minus 2, minus x times x plus 4. Does that look right to you? Okay. Now what? Right here, eliminate those. We can't do that. That would be equivalent to saying 15 divided by 5 equals 10 plus 5 over 5 and eliminating those and getting 10. Is that good math? No, do you see, why can't I do what you said? Well, yeah, only when you have, yeah, if you're, only when you're multiplying or dividing, right? We cannot do that with subtraction or addition. So we can eliminate. So what's another choice besides eliminating those? What's this called? Distributing. So that gives me x minus 2 minus what? Help me out. Anna, help me out. Yeah, plus. That's sort of tricky. Why is it minus 4x? We're actually distributing that negative x, right? So that gives us x, negative x squared minus 4x all over this x minus 3 times x plus 4. Now what? Is there anything else I can do? What's a term? What are terms here that can be combined? Yeah, so how many x's do I have? Negative 3x. Yeah, and I'm going to write this in descending order of exponents. I'm writing it in descending order of exponents because that's standard form. So I have negative x squared, and you said minus 3x, minus 2. Does that look right? Now I'm fine if you want to leave this at the bottom. You want to leave this as a factor. That's okay. The only thing is if you were to look at the back of a book, or because it's multiple choice, your homework is multiple choice, what's considered more standard is if the numerator is written as a trinomial, then the denominator is also written as a trinomial. Yes.
How did the negative 4x go to a negative 3x?
Uh-oh, did I make a mistake? I certainly could have written something down. So where did that happen? Oh yeah, this one here. Is that what you're talking about? So what I have is I have x and then minus x minus x minus x minus x. Is that the same? Is that the same representation? And then these go away, leaving us with negative 3x. Yeah. But Bentley, I certainly make mistakes. So, if I make a mistake, let me know. That one just happened to not be a mistake. Okay, so I'm okay with you leaving it like this. But the only thing is that would be, you have two different forms, right? One is as in standard form and the other is in factored form. And so it's almost like having something like this, 0.5 over 1/2. You have a decimal and a fraction. It feels sort of weird. So you pick one or the other. And so the way that you're typically going to see this written in the back of the book, what was that originally? This x minus 3 was up here, right? Wait, what? Oh, no, just an example. I'm just saying, do you see how this is in standard form and this is in factored form? It would be sort of equivalent to a decimal point and a fraction in the same answer. It feels sort of weird. It's like, give me an answer as a decimal or give me an answer as a fraction. It feels sort of weird to have both, right? Or maybe it doesn't feel weird to you. It feels weird to me. And so I'm okay with this being your answer, but if you wanted, this is how your homework will be written as your choice. It would be negative x squared minus 3x minus 2 over this value of x squared plus x minus 12. X squared, what was it, plus x minus 12? Did I do that wrong? Yeah, there we go. Okay. Questions? Can this be factored?
Yes.
Okay, so first of all, I do want to say I'm okay with this. I'm actually okay with this, but Yeah, let's see. So if I factored it, let's factor out a negative. So I get negative and then x squared plus 3x plus 2, right? So what could it be factored to now? That becomes
X plus 2, X plus 1.
x plus 2 and x plus 1 all over x minus 3 and x plus 4. Yeah, I'm okay with that. Yeah, I'm okay with any of those. All right, so there's one other idea. I know I have less than 10 minutes. Doesn't this class end at 1:15? So I have less than 10 minutes to do this. The other idea, it is called complex fractions. Lots of fractions today. So complex fractions. Complex fractions. What if I have something like this, complex fraction? I have something like 1/3 plus 1/6 over 2/15 minus 3/5. How in the world would you do this? That's not a fraction up there. Where would you start? Let's do the top by itself. Let's just look at this piece right here. Let's just look at this piece here, simplify that, and then look at this piece here and simplify that, and then we'll go from there. Okay. So what do we do to the numerator? Multiply by 1 in the form of
2 over 2.
2 over 2. That gives us 2/6 plus 1/6 over. Do the same thing to the denominator.
It would be 3, 3.
Okay, 3 over 3. That gives us 2/15 minus 9/15. Okay. The numerator is what?
1 over 2.
Yeah, so a 3/6 or 1/2. And the denominator?
Negative 7/15.
Negative 7/15. Now what?
Divide.
When we divide by fractions, here's a tip.
Keep, change, flip.
Nice. When we divide by fractions, here's a tip.
Keep, change, flip.
Yeah, we keep the first one the same. We change from division to multiplication, and then we flip the second fraction. So we keep, change, flip. Keep, change, flip. That's just sloppy. So 1/2 looks like a 7. 1/2 times negative 15/7, which is negative 15. Yeah, there we go. There we go. All right, so now we're going to do, I know we don't have a lot of time. We have 6 minutes to try to do this one. So yeah, are you still copying? We're good? Can move on? Okay, here's what, so this is the idea. I introduced a basic idea with fractions, and now I want to do it with a rational expression. So if I have something like, I want to make sure that it's not too overwhelmingly difficult. All right, so I have 1/2 plus 2x over 2 over x minus 6, I apologize, all over 3x minus 6 over x squared minus 12x plus 36. I would love to give think time, but we don't have time for think time. So maybe it would be worthwhile to watch this last part again and then pause it and see if you can figure it out yourself. Bryn, quickly, where would I start with this?
You want to get rid of the double fraction, so multiply by 1 in the form of x squared minus x plus 36.
Let's look at the numerator. Let's look at the numerator separately.
You first want to I am.
I'm gonna multiply by 1 in the form of x minus 6 over here, over x minus 6.
Okay,
Okay,
so first,
over here, I need to do what?
multiply for, one, multiply one and over two.
Correct. So in the numerator, I have x minus 6 over 2 times x minus 6. We have to have the same denominator. Yeah, my suggestion is you go back and watch just this tail end of class and pause it and see if you can do this on your own. What does this piece here become?
Becomes 4 over 2 times x.
Okay, we have the same denominator, right? Okay, any suggestions of what we can do with the denominator just to save steps?
Factor.
Yeah, factor. Can I factor anything in the numerator?
3 and x minus 2.
Okay, 3 and x, what is it?
Minus 2.
Minus 2. What about the denominator?
X minus 6 and x minus 6.
X minus 6 and x minus 6. Okay, now we're going to do we're going to try to do 2 steps in one just to save time. The first step is we're going to add the numerator. And the second one is we're going to keep, change, flip. So are you okay with 2 steps in one?
Yes.
First step is we're going to add the numerator. And the second step is keep, change, flip. Okay, so my next step, again, I encourage you to watch this again and try to do this on your own. And then push play and see if you did it right. All right, so I'm going to add the numerator. So I have x minus 6 plus 4 over 2 times x minus 6 times, so we keep, change, flip. So that's going to give us x minus 6 times the quantity of x minus 6 over 3 times x minus 2. Is that too sloppy? Try to clean that up a little bit so it's more legible. Okay. Now what?
We cancel an x minus 6 on both sides.
Cross simplification. Yeah, we can cross out an x minus 6 on both sides. Is that it?
There's one more thing you can do, which is was simplify the numerator first. First thing. Numerator.
Simplify the numerator.
Yeah.
This numerator here,
No. That one.
this here.
Yeah.
What can that be simplified to?
X minus 2.
X minus 2. So what I'm left with is this. This is all x minus 2, just to avoid having to rewrite it again.
Simplify out the x minus 2s.
Yeah. So cross simplify the x minus 2.
Yeah.
Does that make sense, or am I skipping too many steps?
That makes sense.
Am I skipping too many steps?
No.
Good. Okay. So what's left over?
X minus 6 over 2.
X minus.
Oh, wait, x minus 6 over 2.
What happens? X minus 6. What happened to this?
You forgot to cross out the bottom one with that one.
Let's see. What did I do? So I crossed that one out, and then I forgot to do that one.
Yeah,
So that's x minus 6 over 2. There's something I'm missing.
3. 6. 3.
X.
Cannot be equal to 3.
Oh, did I forget a 3?
Yeah.
So this should be 6.
And it can't be
X can't be what?
6. Yeah.
It can't be 6 or 2. Okay. Nice. There we go.